This week we're going to look at the simplex algorithm, which is a matrix-based algorithmic method for determining the solution to linear programming problems. And the basic idea of the algorithm is that you start at one corner of the feasible region and you move from corner to corner until you find the corner at which the optimal solution is attained. And the corner that you start with is the origin, provided the origin is indeed a corner of the feasible region, and that will be the case for the problems we'll consider this week, and next week we'll look at the case where the origin is not a corner. And the idea is to first introduce slack variables, and they take up the slack in the left and right hand side of the inequalities. So here we might have three inequalities that are involved as the constraints in a linear programming problem, and we introduce slack variables S1, S2, S3 and change the inequality signs into equality signs. Because the left-hand side is less than or equal to the right-hand side, the thing that we're introducing is going to be non-negative. So all these new variables will be greater than or equal to 0. Now, this process involves concepts called canonical form and basic variables, and you can read about them in the printed notes. I'm not going to go through that here, just don't have enough time. But the idea is that when you start the process, the slack variables are your basic variables. And as you go through the process of the simplex algorithm, we'll change the basic variables as we go along. We'll have to keep track of which ones are the basic variables. Now, as I said, this week we just look at the case where the origin is a corner of the feasible region, and that corresponds to all the inequalities being less than or equal to some positive number. So for instance here, this is the kind of inequality we're treating this week. Next week, when we have greater than or equal to some positive number, we'll have a slightly different process. Example. Let's look at the basic example from week 1. So this was a system that had 3 inequalities, and we introduced 3 slack variables, and we write the corresponding equations in matrix form. As I said just a minute ago, when we start, our slack variables are the basic variables. And corresponding to those basic variables, we have a basic solution. And that solution is attained by setting the basic variables equal to the corresponding numbers on the right-hand side and setting the other variables equal to 0. So in this case, x1 and x2 are our decision variables are set to 0, and our slack variables are set to 70, 30, and 90 respectively. And then we introduce a new row corresponding to the objective function. Now, in our basic example, the objective function was 40x1 plus 60x2, and the idea is we rewrite that as z minus 40x1 minus 60x2 equals 0, and that corresponds to this new row in this matrix formulation. Here, this is the z column, and this last row is the z equation. And the basic solution that we have, x1 equals 0, x2 equals 0, I just spoke about on the previous slide, this corresponds to the origin. And the number that's in the bottom right-hand corner is the value of z at that point. Now we're going to do a couple of standard notational changes just for convenience. The first thing is that since the first column is always 0, 0, 0, 1, because that's always the case, we don't bother to write it down. We just drop that off. The second thing is we present the expression not exactly as a matrix, but as a tableau. So this is just a fancy name for a table. We put the variable names along the top, and on the left-hand side we write down which ones are currently the basic variables. And we put an extra line across here separating the constraint rows from the Z equation row. Now, as we go through the process, we change the basic variables. So at each stage, we get rid of one of the basic variables and we replace it with a new basic variable. The new basic variable is called the entering basic variable, and the one that we get rid of is called the departing basic variable. Now we need to have rules for doing this, and the rules are as follows. To decide on the entering basic variables, we take the biggest negative number in the bottom row. Now, in this case, here, the biggest negative number is negative 60. It's potential confusion as what we mean by biggest here. We mean, as a real number, the least number. This is usually called the biggest negative number for obvious reasons. So that's in the x2 column. So our entering basic variable is x2. To determine the departing basic variable, we look at the ratios of the resource values divided by the numbers in the column of our entering basic variable, and we look for the least of the positive ratios. So here, this means we look at the ratio 70 divided by 1, 40 divided by 1, 90 divided by 3. Now 90 divided by 3 is 30, is smaller than the other two ratios, and that determines the departing basic variable. It will be S3, will be the departing basic variable, and we put a little circle or square around this number, which corresponds to our choice of entering basic variable and departing basic variable. So that's, in our case, S3. Okay, and now we have to do some matrix operations. So what we do is we take that number that we had to circle or square around, we divide each row by that number in order to convert that number in the circle or square into a 1, and then we use that one to eliminate everything else that's in that column. So this is one of the standard matrix operations that you're used to using in the Gaussian algorithm, assuming you've seen the Gaussian algorithm before. So in our case here, we had our special number was in this position, and we turned this into a 1, and then we used the rows, that row, to clear out everything else in this column. And if you go through it carefully, you'll find that this is the matrix we get. So this is the 1 that's been produced, and that 1 has been used to get rid of everything else in this column. Now you'll notice there's fractions appearing. You have to work with fractions. Don't write your answer as decimals. If you have any trouble with it, after a little bit of practice, I'm sure you'll be fine with it. Okay, and at this point, we now have our new basic variable is x2. So our basic variables are s1, s2, and x2. That gives us the basic solution. 30 for x2, 40 for s1, 10 for s2, 0 for x1 because it's not basic, and 0 for s3, so it's not basic. That gives us a solution corresponding to the corner 0, 30 of our feasible region, and that z value at that point is this one here. So the idea then is we just repeat this process. We keep on doing it. We do exactly the same thing. We find the entering basic variable, the departing basic variable. We locate that special entry, and then we pivot on that entry. And when we do it a second time, we'll get this matrix. This is this tableau. And at this point here, we stop the process. We stop the process because, well, we can't continue. There are no more negative numbers in the bottom row, so there is now no way to continue on. So I encourage you to go through this calculation, make sure you can see exactly how this tableau is produced. You'll have to do things like this, and you'll have to present it in this form, and at each stage writing down the basic variables. So we stop because we can't go on, and so this point that we found is the solution, and indeed it is the solution that we obtained using the graphical method in chapter 1. It is possible that the algorithm might stop for another reason. It could stop because you can no longer apply the entering so the basic way is that you can't apply the entering basic variable rule because there's no negative numbers in the bottom row, but it could also apply because you can't apply the basic variable rule. So this happens when all the ratios are negative. Remember, we're looking for the smallest non-negative ratio. One other little aspect to it is that it could be that there's more than one solution. We've seen examples of that in chapter 1, and this happens, this general feature where you have more than one solution is called non-uniqueness, and it can happen if there's a zero entry in the bottom row in a column of a non-basic variable. And we'll see examples of this in the practice class. When you get such a situation, you just continue on by working in that column, and you get that will lead you to the other solution. So you can read about this in the notes, and we'll look at it in the practice class. So in summary, here's the Simplex algorithm written out in all its details. You apply, you do it repetitively. At each step, you look for the biggest negative entry in the bottom row. Then you compute the ratios. You only look at the entries that are positive, and you choose the smallest non-negative value. You repeat until you can't go on any further, which could happen because you can't apply the entering basic variable rule, or you can't apply the departing basic variable rule.